This is my alternate assignment for the Eutrophication data lab. So, data from 2 agricultural runoff simulations were analyzed to model eutrophication and its impact on dissolved oxygen. Site A represented heavy fertilizer runoff, while Site B represented reduced runoff using best management practices. Dissolved oxygen in Site A declined from 9.8 milligrams per liter to 0 milligrams per liter over 20 minutes, while Site B declined more gradually from 9.8 to 5.1. Site A crossed the first stress threshold early in the trial, while Site B remained above it throughout. These results supported the idea that high nutrient loads accelerate eutrophication, increase biological oxygen demand, and create hypotoxic conditions that could lead to fish kills. So this brings us to the purpose and discussion of the concepts. So the purpose of this investigation was to determine how nutrient load from agricultural runoff affects dissolved oxygen levels in aquatic systems and compare the rate of oxygen depletion between heavy and reduced runoff conditions. For the discussion of concepts, there's 4 concepts. The cultural eutrophication is the process by which human activities introduce excessive nutrients, primarily nitrogen and phosphorus, into aquatic systems. These nutrients stimulate rapid algal growth, known as algal blooms. When algae die, they are decomposed by bacteria, which consume dissolved oxygen during respiration. The next is biological oxygen demand, otherwise known as BOD. This refers to the amount of oxygen required by microorganisms to break down organic matter. This demonstrates that as nutrient levels increase, BOD increases, leading to decreased dissolved oxygen. If dissolved oxygen falls below the approximately 4.0 milligrams per liter line, this means that many fish species experience stress or mortality due to insufficient oxygen for cellular respiration. The next concept is hypoxia, which occurs when dissolved oxygen levels become too low to sustain most aquatic organisms. Hypoxic zones, often referred to as dead zones, are commonly observed in these areas that receive heavy agricultural runoff. The last is dissolved oxygen, and this is the concentration of oxygen gas dissolved in the water, and this is essential for aerobic aquatic organisms. And the 3 sources that I used are the United States Environmental Protection Agency, the National Oceanic and Atmospheric Administration, and the U.S. Geological Survey. Next is the hypothesis in scientific design. So my hypothesis is that if a water system receives heavy nutrient runoff, then dissolved oxygen levels will decrease more rapidly and reach lower concentrations than a system receiving reduced nutrient runoff. For the scientific design, the independent variable was the nutrient load, heavy runoff versus reduced runoff. The dependent variable was dissolved oxygen concentration, which is measured in milligrams per liter, and the constants were the volume of water, the measurement intervals, which was 2 minutes, the total duration, which was 20 minutes, type of dissolved oxygen probe, and environmental setting. The control was that the reduced runoff condition site B functioned as the comparison baseline, representing best management practices. And for the materials and safety, we used warm water, whole milk, 1% milk, yeast solution, 2 beakers, dissolved oxygen probe, thermometer probe, and a timer. And the safety was that standard laboratory safety procedures were followed. Eye protection was worn during the investigation, spills were cleaned immediately to prevent slipping hazards, and electrical probes were kept dry except for sensor tips. So next was the procedure. We followed the procedure that was on the alternative lab, which was warm water and milk were combined to simulate agricultural runoff conditions. Yeast was added to both samples to simulate bacterial decomposition, and dissolved oxygen levels were measured at 2-minute intervals over a 20-minute period using a dissolved oxygen probe. The data was recorded and later analyzed. And a modification we added was that the yeast solution used for Site A had been left at room temperature longer than Site B prior at the start of the data collection. So this is my drawing, the representation of the lab, and the experiment modeled agricultural runoff entering freshwater ecosystems. So one of these is whole milk, and it represents heavy fertilizer runoff containing high nutrient concentrations, and the other was 1% milk, represented reduced nutrient runoff using best management practices. Yeast simulated bacterial decomposers responsible for increasing biological oxygen demand, and dissolved oxygen measurements were represented oxygen availability for aquatic organisms. So the data table that we used was the data that was given to us. So this was the 20 minutes, and these show the time. This shows site A, and this shows site B. And then this shows all of the data for the lab. And this is my calculations, this is the formula I used, which is the initial dissolved oxygen minus the final dissolved oxygen over the 20 minutes. That is the rate. And then the initial dissolved oxygen was 9.8, the final was 0. So the rate was 0.49 milligrams per liter per minute. And then that was for site A. For site B, it was 0.29. And this was the graph that we created based off of the data that we received from the graph. So this brings us to the discussion, which is the application, the error analysis, and the conclusion/improvements. So for the real-world application, this says, when does site A become uninhabitable for fish, which is applicable to the real world? So the fish threshold for dying is 4 milligrams per liter. And from the data, at 6 minutes, at site A, the dissolved oxygen was 4.2, which was a little bit above the threshold. And at 8 minutes, site A, the dissolved oxygen was at 2.5, which was below the threshold. And using the discrete data points, the first time recorded at which site A was clearly below 4.0 milligrams per liter is at 8 minutes. In a real water body, fish would begin to experience severe stress as dissolved oxygen approached 4.0 milligrams per liter, and many species would be unable to survive once dissolved oxygen dropped into the 2 to 3 milligrams per liter range. Next is the error analysis. So one error was that the temperature probe fell out at minute 12 at site B. So when the temperature probe fell out of the beaker, the recorded temperature after that point may not have been accurately reflected of the water temperature. And because water temperature affects dissolved oxygen solubility and microbial respiration, any misreading could complicate the interpretation of the relationship between its temperature and dissolved oxygen. However, the dissolved oxygen probe data for site B still shows a smooth, gradual decline. So the main dissolved oxygen trend is still likely valid, but the error mainly weakens any conclusions about temperature effects. Another error we found was that the yeast solution for site A had been sitting out for 20 minutes longer. So the yeast for site A was left out for 20 minutes longer than site B. And during that time, the yeast cells could have been more metabolically active or began consuming oxygen even before being added to the beaker. This would mean that at the start of the experiment, site A effectively had more active decomposer community than site B. As a result, the rate of oxygen composition in site A may have been artificially inflated, making dissolved oxygen drop faster than it would have if both sites had equally fresh yeast. This reduces the validity of the comparison because the difference in dissolved oxygen curves is not solely due to nutrient load, which is the milk fat/fertilizer level. And it is also influenced by unequal microbial starting conditions. And this impacts the comparison because the experiment was designed so that the nutrient load would be the only major difference between site A and site B. If the yeast is different, then it changes it completely. And because of the yeast, we likely have overestimated the effect of the nutrient load alone. And therefore, while the data still supports the hypothesis that heavier runoff still leads to faster dissolved oxygen depletion, the magnitude of the difference between site A and site B is somewhat exaggerated by this procedural error. And lastly, this is the conclusion. So the analysis of dissolved oxygen data from 2 simulated agricultural runoff sites shows that heavy nutrient load, which was in site A, causes a rapid decline in dissolved oxygen. This led to hypoxic conditions and potential fish kills, while reduced nutrient loading in site B maintained dissolved oxygen at healthier levels. So despite procedural errors that likely exaggerated the rate of oxygen loss in site A, the overall pattern supports the hypothesis that cultural eutrophication increases biochemical oxygen demand and drives oxygen sag. A specific best management practice that Site B likely used is the implementation of a riparian buffer zone. And this is strips of vegetation along waterways that trap and absorb nutrients before they can reach streams or ponds. Such BPMs can significantly reduce nutrient runoff, slow eutrophication, and help maintain dissolved oxygen levels suitable for aquatic life. And thank you, that is the lab.